All right, here we go. I'm going to have to move through this fairly quickly to make sure we get to all of it. So yesterday we talked about strong acid, strong base titrations. Okay, and that's fairly straightforward. You're adding usually a strong base to a strong acid. That's the typical way that it is done, at least in your introductory chemistry classes. And the graph for that would look like this bottom line right here that starts at a pH of 1. Okay, so you've got a really steep slope up to your equivalence point, and notice again that it doesn't matter what indicator we use because both of these are basically in the same place on the graph, right? Now, for comparison, we kept that on there, but the one that we really want to look at now is the weak acid strong base titration. Okay, and so notice there's a few differences here. Okay, first difference is, and they ask this question often on the AP exam, how can you tell this is a weak base? And I'll show you a graph of a titration. Okay, but they'll give you some data about a titration. Or how can you tell this is a weak acid? You know, either one. And so what you're going to say, one of the things that you're looking for is the pH that it starts at. All right, this initial pH is much higher than the pH of the strong acid, strong base that we were talking about before. Okay, so that's one thing. And then what else do you notice about this curve? Okay, this slope is just a tiny bit steeper right here, and then, you know, the equivalence point is reached at a much higher point. Okay, because your equivalence point here would be around 7, or it should be right at 7 for strong acid, strong base. Okay, but your equivalence point is going to be above 7 if you're doing a weak acid, strong base titration. Now, we're not going to talk. We're just going to assume everything's the opposite for a weak base, strong acid titration. So in that instance, obviously this graph would be reversed. Okay. But what would be the pH of a weak base, strong acid titration? You don't have to tell me an exact number, but for a weak base, strong acid titration, you'd expect the pH to be below 7, right? Okay, so that's kind of how that works, and it should make sense. I mean, it makes logical sense that if you put a strong base with a weak acid, then you're going to have a pH above 7, and if you put a strong acid with a weak base, you're going to have a pH below 7. Okay, so the other thing I want you to notice here, only one indicator is going to work in this particular situation, right? Which indicator can we not use anymore? The methyl red isn't going to work anymore because that's not that close to our equivalence point anymore. Does that make sense? Okay, so we can't use that one. All right. So this is a type of titration where strong base is added to weak acid. And again, we have 4 stages in this type of titration, just like we did in the strong acid, strong base titration. To find the initial pH, in stage 1, you're going to find the pH of the weak acid. Okay. Now, how do we do that? You have to use an ice table, right? Okay, so this is basically what we learned in the last unit. So the example here, what's the pH of a 0.1 molar HC2H3O2 solution? And again, just for the sake of time, because we've done so many of these, I think I'm just going to skip right to the part where we talk about the way that this equation gets set up. And once again, I am very bad. I do acetic acid so much, I should have this memorized, but I always get it scrambled with the HF for some reason. And you're not going to have to memorize these. They will give these to you in the AP exam, so I'm not too big of a hypocrite there, I guess. Alright, so let's see. Acetic is 1.8 times 10 to the negative 5th. Okay, so once you set up your ice table, which again, I'm just kind of skipping for the sake of time here, you're going to end up with 1.8 times 10 to the negative 5th is equal to x squared over 0.100. Okay? And we're all very familiar with that process, right? Are we okay with skipping that? Alright, so then once you solve this, you're basically just solving for x. So 1.8 times 10 to the negative 6th is what you're going to end up with, and then you take the square root of that. You get 0.00x is equal to 0.00134, something like that. that is going to be our H plus concentration in that solution. So then we take the negative log of that number, and that'll give us our pH, our initial pH. So at that concentration, our initial pH is going to be 2. We need 3 numbers after the decimal here. 2.872. Okay. Because we had 3 sig figs in our original number. So that's how you do that, okay? That's fairly easy. That's just, that's when we only have acetic acid in the solution, okay? Everybody all right with that? Okay. Stage 2. That's when we have added some of the strong base, but we're not to the equivalence point yet, okay? So in stage 2, we've got the reaction for the neutralization of acetic acid with a strong base. This is similar to what we were doing when we were talking about buffer solutions the other day, where you're adding a strong base to a weak acid. All right. So we're adding. Did we specifically say here what we're adding? I don't think I did specifically say. Let's assume it's an AOH. Okay. Oh wait, did I give an example? We're gonna have an example, but it doesn't matter what it is, okay? Unless it matters a little bit, because if it's like something like calcium hydroxide, that's CaOH2, right? So then we would have 2 OH minuses for every one of those. But let's assume that we're just using sodium hydroxide. That's what we usually use as NaOH. So then the reaction for the neutralization of the acetic acid, we've got OH minus that we're adding to that solution. And that solution, the OH minus is going to react with the acetic acid. We're doing well this morning. So what is that going to produce when those two things react? It's going to produce water and acetate. Okay, H2O and the acetate ion, C2H3O2 minus. Okay? And again, this is just a forward arrow. Why? This is a strong base reaction, okay? So this is not an equilibrium. This OH minus is going to react with the acetic acid until it's all gone, until the OH minus is all gone, or until the acetic acid is all gone. Okay? One of the two. So that's your reaction there. So we've got 2 steps to calculate the pH at this stage. And this is basically just like what we talked about yesterday at the very beginning. Okay, stoichiometry first, equilibrium second. So you have to use the stoichiometry to figure out how much of the acetic acid are we going to have left over at the end. Okay, now how do I know that I'm going to have some acetic acid left over at the end with this type of calculation? Well, not necessarily. In the course of a titration, eventually there's going to be more OH minus, right? But where are we in this titration right now? We're before the equivalence point, right? Because we're between the initial and the equivalence point. So we haven't gotten to the equivalence point yet, which means we haven't added as much OH minus in there as we have acetic acid, okay? So stoichiometry first, equilibrium second. So stoichiometry, we've got to figure out how much acetic acid is left after we use up all the OH minus. And then we're going to use that to calculate, then we're going to use that for our equilibrium to figure out what the pH of the solution is now. Okay? So here's an example of that. No, I don't have an example of that. Why do I not have an example of that? I think I have one at the end, I hope. Because we need to talk about that. So then at the equivalence point, you're going to calculate the concentration of the conjugate base that gets formed, and you're going to use that to figure out the pH of the solution. Okay, so this is hopefully going to explain why at the equivalence point the pH is actually a little bit higher than 7. All right, so here's your example. We're adding 50 milliliters of 0.1 molar NaOH to 50 milliliters of 0.1 molar acetic acid. Okay, so again, we just wrote the reaction for this. It's going to be OH minus plus HC2H3O2. And that goes to H2O plus acetate. Okay? And again, for stoichiometry, we want to talk about moles. So the OH minus here, how many moles of OH minus do we have in this solution? We did a similar calculation yesterday. Does that help? So we've got a volume, we've got a concentration, right? Then we need to change that volume into liters, so it's 0.050, I guess 0.0500 liters. And then we multiply that by the 0.1, so it's going to give us 0.005, right? Yeah, that's right. 0. That's the number of moles of OH minus we have. Well, we don't have to do the same calculation again. It's the exact same numbers for the acetic acid. 0. Okay. Now this solution initially didn't have any acetate in it, right? Because this is just an acetic acid solution. Now there might have been some in there, but we're going to assume that the amount that we had in there from the equilibrium from this dissociation probably is insignificant compared to the amount that we're going to form when we add this OH minus. Okay, so we're going to assume that relatively we didn't have any of that. Okay, not entirely true, but it's true enough for our calculation. So then these two are both going to decrease by the same amount because these two are going to react with one another to completion, right? Because this is a 1-to-1 ratio here. So minus 0.00500 minus 0.00500. And you end up with none of these, and this is going to be plus 0.00500. So we end up with this for our number of moles of acetate at the end. Okay? So far, so good? All right, now what we have to realize is you have to think about this happening in two steps, okay? Now, it's going to be a little more simultaneous than this in the actual solution, but it's helpful, I think, if you break this up into a couple of steps. So step one, the OH minus reacts with the acetic acid to make the acetate. What happens then? What's the acetate going to do in the solution? It's going to react with the water in an equilibrium to produce a little bit of acetic acid and some OH minus, right? So we know that reaction. That's everyone okay with this? If I erase it, because I need some room here. I need to keep this number though, so don't forget it. Alright, so now what we've got is C2H3O2 minus. It's going to react with the water. Now this is an equilibrium because this is a weak base, okay? But it's going to pull a hydrogen off of the water, make HC2H3O2 plus OH minus, okay? And now, again, when we're doing equilibrium, you want to use concentrations. And honestly, most of the time concentrations would probably, see where concentrations are going to get you into trouble. This is why you have to worry about this with the stoichiometry, is because if your volumes change at all, then that's going to mess you up. Okay, so it really is a better idea to use moles when you're doing stoichiometry, and then use concentrations when we're talking about equilibrium. Okay, so on this one we have 0.00500 moles of acetate, but what's our total volume of solution here? It's 100 milliliters or 0.1 liters, right? So if we take the 0.00500 moles of the acetate that we have and we divide it by 0.1 liters, then that gives us a concentration of 0.0500 to begin with, okay? Now, we just used up all of the acetic acid because we reacted it with all the OH minus. So then, once that happens, we really have none of either of those because they both just, reacted with each other to make the acetate, right? So then, you do your typical minus x, plus x, plus x. And then you should be able to, again, if we have the Ka for acetic acid, or I guess in this case what you would need would be the Kb for the acetate ion, okay? In order to plug into this, because this is the base reaction, so our Ka is 1.8 times 10 to the negative fifth for acetic acid. So our Kb would be, let's see here, 5.6 times 10 to the negative 10th. Okay, and so then we can use that. 5.6 times 10 to the negative 10th is equal to x squared over, and again, that's a very small number, so we can assume our x is pretty small here, even though our concentration is fairly small as well. So then you just work that out, solve for x. And our x, again, our x is very small. It's 5.2 times 10, or 5.3 times 10 to the negative 6th. Okay. That is our OH minus concentration in this new solution, right? So we have a little bit of extra OH minus being made now because we made a weak base in that solution, ultimately. And so then if you take the negative log of that number, that's going to give you your POH, okay? Your POH ends up being 5.28. So then the pH, just take 14 minus that. That's going to be 8.72. Okay? Now just as you go through this process, stop and check whether your numbers are making sense, right? We just titrated a weak acid with a strong base. Does it make sense that at the equivalence point our pH would be higher than 7? That makes sense, right? So if you forget this is a POH and you end up with 5.28, that should be a red flag. Wait a second, why is this pH under 7? Because this is a weak acid strong base. And then that might jog your memory. Oh, that was a POH I just found. I need to subtract that from 14 to get the pH. Okay? So that's a long process. Okay, there's a lot of calculation involved with that, which is why, I'm giving you lots of free response practice on these, because you need to be able to go through these fairly quickly, and oftentimes you will get something along these lines. Okay. All right. The pH, we just talked about this, of a weak acid strong base titration is always going to be greater than 7, okay? Because what we are forming after we react the weak acid with the strong base, we're forming a weak base as a product of that reaction. So then that weak base is going to do weak base equilibrium and raise the pH of the solution a little bit, okay? After the equivalence point, well, there are kind of two sources of OH minus at that point. We're adding strong base still into the solution, but then we've also got this weak base equilibrium that's going on right here. The acetic acid making a little bit of OH minus. Okay, which do you think is more significant? The strong base we're dumping in. Okay, in fact, I mean, look at this X, 5.3 times 10 to the negative 6th molar. That's a very small amount of OH minus that's being produced in this solution, right? So the assumption that we typically make is that the pH is going to be determined solely by the amount of OH minus we're dumping into this thing from the strong base. So you can kind of, after the equivalence point, you can ignore the equilibrium that's happening here, okay? Because what's really changing the pH after the equivalence point is the strong base that we're dumping in. Does that make sense? Okay, so because the weak acid has been neutralized, the OH minus concentration determines the pH. So an example of that, if we add 51.0 milliliters of 0.1 molar NaOH to 50.0 milliliters of 0.1, that's just a lot of numbers. And I didn't leave myself very much room for this. Do I have room on the next page? No. Okay, tell you what I'm going to do. I'm going to use the next page to calculate this one, just for a second. So we've got 51 milliliters of 0.1 and 50 milliliters of the 0.1. Okay, so this is the same reaction. Right, so we still got our OH minus here, and we're adding it to the acetic acid. And this is going to make water and C2H3O2 minus. Okay. But we are now adding 51 milliliters of the 0.1 molar NaOH. So instead of the 0.00500, it's going to be 0.00510. Did I do my math right there? It was 0.0050 before, wasn't it? Okay. And then this is 0.00500. Okay. And then again, we're going to assume that we don't have any of that to start with. Not entirely true, but true enough. So now what's going to happen? They're not equal, so what kind of problem do we essentially have now? This is a limiting reactant problem, right? Okay, so we're thinking, we got to be thinking about which one's going to run out first, and actually in this case, the acetic acid's going to run out first. Okay, so both of these are going to go down by 0.00500. This is going to go up by 0.00500. And now we've got a really small number here. Okay, but again, what I was saying before is we don't care about this. Yes, there is a little bit of that in solution, and yes, it is going to be doing equilibrium and making a little bit of OH minus, okay? But that's really nothing compared to the OH minus that we just dumped in, because if you look back to our concentration here, this was 5.3 times 10 to the negative 6th, okay? The OH minus we just put into this solution, the extra OH minus, is going to be 1 times 10 to the negative 4th, okay? So quite a bit more concentrated here than there. And actually, this is the number of moles, I'm sorry. So it's going to be even more, because to figure out the actual concentration of the OH minus, what do we have to do? We have to divide it by the volume, right? So this is going to be 0.00010 moles of OH minus in how much solution? 101 milliliters, or 0.101 liters. Okay. So again, I guess that's the one thing that I don't like about using ice tables for this, is that it would be very easy to forget that you're actually doing this in moles. So maybe it's better to just make sure you're labeling everything here, so that we can keep track of what we're doing. Okay? So then once you do that, now our concentration's even higher, right? Now it's 9.9 times 10 to the negative 4th molar. Okay, and that's our OH minus concentration after this reaction has taken place. Okay, so then how do we figure out the pH of the solution? Just take the negative log of that. That's going to give us a POH, right? And then we subtract that from 14. So the negative log of that is going to be about 3.00. So our POH equals 3.00. So then our pH would be 11.00. And again, I mean, just notice how big of a difference that makes, because At the equivalence point, our pH is 8.72. If we add 1 more milliliter of the sodium hydroxide, just 1 more milliliter, then now our pH is at 11. Okay, so that strong base really does have a huge impact on the solution. That's why we can kind of ignore the effect of the acetate in this case. Okay? Alright, calculate the pH at the equivalence point and the titration of 50 milliliters of 0.1. Why did I put that on there? That's the exact same thing we just did, isn't it? No, it's 0.100 molar NaOH. Oh, does it? Oh, okay, maybe that's why, because it's... There we go, okay. pH at the equivalence point. How many more problems do we have after this? Two more. Okay, yeah, and this one, it's not really a problem even. Okay, I think we have time for this. But I need to... Let me make it match what's on your sheet. So on your sheet... Oh, right. Okay, there we go. Whew. I totally forgot that this was not the problem we were doing. See, if you guys hadn't been here, I just would have totally skipped that problem on accident. And this is the one that I wanted to go over because this is the one before we get to the equivalence point, okay? So we're adding 45 milliliters of the 0.1 molar NaOH. What's that? The first one was this one. The example here, the addition of 51 milliliters of 0.1. The one before that? No, that's 50 milliliters. Sorry. No, this one is at the equivalence point. The 50 milliliters adding to 50 milliliters, that's at the equivalence point. And then we did one that was an example after the equivalence point. Okay. This one right here, this is actually before the equivalence point, which I don't know why I didn't put this one in while we were talking about that, but here it is, okay? So this one is before we get to the equivalence point, okay? You should have a blank section there where you can work this one out, okay? So, the only difference on this one is we have a different limiting reactant, right? Which means, unfortunately, we are going to still have some equilibrium at the end of this thing. But it's still the same reaction. We've still got OH minus. Oops, keep doing that. Okay, so now, again, and I'm going to write moles on this one because we're doing our stoichiometry first, and then we have to think about our equilibrium second, okay? And again, just going back in the process, it would have been much better if I had just put it here in the process, but this is at stage 2, okay? This is before we get to the equivalence point, but we've started adding some of the strong base at this point, all right? So this is where you got to remember this: stoichiometry first, equilibrium second. Okay. And you just kind of have to think about what's happening here, and hopefully that'll sort of guide the process. So we've got here we're going to have 0.00450 moles of the OH minus, and then we've got 0.00500 moles of the acetic acid. And then again, we're assuming that we don't have any of this to start with. Okay? So at this point, what is our limiting reactant here? What's going to run out first? The OH minus, okay? Before the equivalence point, your OH minus is going to run out first. So again, because this is a 1-to-1 stoichiometry, then 0.00450 moles of the OH minus is going to react with 0.00450 moles of the acetic acid to produce 0.00450 moles of the acetate. All right, so then you end up with none of the OH minus, and then you end up with, I should do this in my head, I'm ashamed. Thank you. Okay, well, now what? Because now we have some of the acetate and some of the acetic acid left. What is this if we have some of the acid and its conjugate base in the solution? Ah, it's a buffer. So what can we use for a buffer solution? Henderson-Hasselbalch equation, okay? So that's going to be the easiest way to solve this one. Now, the only thing you have to be careful of here is we need to use concentrations, not moles. Okay? So, and that's why I was a little bit more careful labeling this time, so that hopefully this sets up a red flag in your head. Oh yeah, we got to plug in concentrations here. So what is our volume of this solution? It's 95, okay? So again, you got to watch that carefully. So 0.005, oops, not enough zeros. Divided by 0.095 is equal to 0.0053. That's our concentration of the acetic acid. Okay, and then I have to do the same thing over here. 0.00450 divided by 0.095. 0.047. Okay, so is this a very good buffer solution? It's not great. I mean, the concentrations are not that equal. There's actually quite a bit more of the acetate in here than there is of the acetic acid. Okay, but we can still, there's still enough of it that we can use Henderson-Hasselbalch for this. So that's, again, when you can use it, do, because it's quite a bit easier than setting up an ice table and doing that whole calculation. Maybe not quite a bit easier, but I think it's easier. So then your pH is equal to the pKa. Now the Ka is given to us here, 1.8 times 10 to the negative fifth, finally. Which is 4.74. Plus the log of the base concentration over the acid concentration. Okay, the base concentration is right here. Probably should have labeled these. 0.047 divided by 0.0053. Okay. So then we just plug this in. I'm getting a pH here of 5.6. How many sig figs do I need? 5.688. Okay, at this particular point. Now again, let's just stop and think about whether this makes sense, okay? If these two concentrations are equal, the concentration of the acid and its conjugate base are equal, that means pH equals pKa, right? So then the pH would actually be 4.74. But now we have more base in the solution, more of the weak base than we do of the weak acid, so we would expect the pH to be a little bit higher than 4.74, right? So it makes sense that our pH is 5.688. Okay. So that's how you do that. So again, just to sort of run you through the steps here, because this is kind of the tricky part here. Okay, so step one, if you're just talking about initial pH before any of the strong base gets added, you just do your normal ice table. Okay, just like we did in the last unit. Step two is just like what we just did. Okay, you're going to run out of OH minus. That means you're going to have some of the acid and its conjugate base. Then you're going to want to use Henderson-Hasselbalch to figure out the actual pH at that point. At the equivalence point, you have now used up all of the Yeah, okay, so I erased the first part of this, but you've used up all of your OH minus and all of your acetic acid at that point, so you have 0 of those, but you're going to have some of the conjugate base. That conjugate base is going to start doing equilibrium, so you need to do another ice table for this to figure out your concentration of your OH minus, and then find the pH from there, okay? And then the last step here, we're just going to assume on this last step that the OH minus coming from the strong base is what determines the pH. So find out how much OH minus you have left over, and then use that concentration to figure out the pH. Okay, so those are your 4 steps there in the titration. All right, calculate the pH at the equivalence point. I don't know why that's on there, because we already did that, so we're skipping that. All right. So let's talk again, and we talked about this at the beginning when we looked at the graph, but now you're just getting it in writing, okay? There's certain ways that a weak acid strong base titration is going to be different from a strong acid strong base titration, okay? First of all, you're going to have a higher initial pH, all right? So that's one thing that you're always looking for here. What's the pH that I'm starting at? If it's really low, like, you know, between 0 and 1, or, you know, usually it's 1 or below, then that's going to be probably a strong acid. If it's higher than that, a 2, a 3, or a 4, that's a big clue it's a weak acid that we're starting with, okay? The pH change at the rapid rise portion of the curve is going to be a lot smaller. So, again, you're already starting high enough that that big spike in pH is not going to be as drastic for a weak acid strong base titration. And then the pH at the equivalence point is always going to be above 7 for a weak acid strong base titration, okay? Weak acid strong base titration. We're not going to talk a lot in here about weak acid, weak base titrations. So, again, the way the graph looks just really sort of depends on the Ka for the acid that we're talking about, okay? So the smaller the Ka, the less drastic this curve gets, right? And the higher the initial pH is going to be, so hopefully that makes sense. Down here, this is your strong acid down at 1 or so, okay? That's where you get the steepest curve, that's where you start at the lowest pH. Okay. So, there's a smaller range here. We also talked about this. It's more important with a weak acid strong base titration to pick the right indicator. You need an indicator that's going to change color at the right pH, okay? And so we're actually going to do a lab on this where you choose an indicator that you think is going to work for particular reactions. And that one's kind of fun because you have a bunch of different indicators that turn different colors at different pHs, so that one's fun. And then just a quick mention on the weak base with a strong acid titration. It's going to be exactly the opposite of what we just talked about, okay? So it's the same exact process. It's just opposite of the process we just talked about. Now normally we titrate, we start with an acid and then we add base to it. That's typically the way a titration is done, but not always, okay? So if we did it the opposite way, then the pH at the equivalence point is going to be lower than 7. Okay, and we already talked about that as well. So that's what a graph would look like for a weak acid, a weak base strong acid titration, okay? Now this one up here, that's a strong base strong acid titration, okay? And we already talked about that one. So then just for comparison, again, notice the weak base, pH is a little bit lower, okay, to start out with, and that curve is a little more drastic. And in this case, methyl red would be our choice, not phenolphthalein, because our equivalence point is going to be below 7. Does that make sense? Okay. And then just very quickly about polyprotic acids. If we have more than one ionizable hydrogen, then it's going to react with the OH minus in a series of steps, okay? So H3PO3 being neutralized with the sodium hydroxide really you can kind of think of this as happening in a series here. So you've got the OH minus reacting with the initial H3PO3 to make water and H2PO3 minus. Okay. And then if you keep adding OH to the solution, OH minus, then obviously then our second step would be the OH minus is going to react, some of that is going to react to the H2PO3 minus to make more water and HPO3 2 minus. Okay, and then again, if you keep adding OH minus, then that's going to react with the HPO3 2 minus, convert it into PO3 3 minus. Okay, so you can just think about that happening in a series of steps. So any ideas with the graph or do you already have the graph on your paper? You don't. Okay, any ideas with the graph? Okay, any ideas what the graph for that one might look like? Okay, so we're basically going to have 3 different equivalence points here, right? An equivalence point for the first H plus that comes off, then an equivalence point for the second one, and an equivalence point for the third one. So your graph is actually going to look a little something like that, okay? Now, by the time you get to your third equivalence point, this is such a weak acid at that point that you really can't even see the spike in pH at that point, okay? And now it's just kind of like, it doesn't even matter. We're just adding OH minus to the solution. It's increasing the pH, okay? But you can definitely see it for the first 2. There's your equivalence point, there's your equivalence point, and again, for this last one, technically there's your equivalence point, but that's not going to show a drastic rise in pH by the time you get to that one, okay? That's really all we're going to say with titrations of polyprotics. You're not going to see a lot with that on the AP exam, but I just thought I'd mention it, okay? Alright, so that is that. I think, yeah, we are done. So we'll do a lot of practice on that in class today, tomorrow, and Friday.